So guys, now let's go ahead and understand the maths intuition behind the PCA algorithm. Now over here, let's consider that I have this two axes X and Y and I have just plotted this point. And let's consider that my aim is to convert or reduce from 2 dimensions to 1 dimension. And as you know, the final goal of the PCA algorithm is to find out the best principal component line after the transformation from this axis in such a way that maximum variance needs to be captured. Now let's say for this example, I'm just going to consider this is that specific line, which is my principal component 1. Because as soon as I plot all this point over here, you can see that maximum variance will get captured, right? So that is the reason why we are selecting this as the best principal component line, okay? Now, what PCA is actually going to do in order to come to this conclusion, like whether this is the best or not, there are two important things. One is projections, and the second thing is the cost function that is related to the variance. Okay, so let's go ahead and discuss about both of them. Okay, so out of all these points, let's do one thing. Let's take up one point, and for now I can just consider this is my point P1, okay, which is denoted by x1 y1. Okay, this is obviously denoted by x1 y1 because why? This is my x-axis, this is my y-axis. So let's say this is denoted by x1 comma y1. Okay, so I can consider also this P as a vector. Okay, so let's say that this is a specific vector and this P1 is a vector. And let's consider that we also have a unit vector, which is specifically given as u. Okay, so this is my unit vector. Now, the first point, let's go to the first point. The first point is all about projection. So let's say that if we really want to project this P1 into this particular point, okay, into this particular vector, then we will get something called as P1 dash. Now, we really need to find out what is this new projection, because see over here, our main aim is to capture the maximum variance. The maximum variance will only get captured when all the other points that you will be seeing in this, right? Once we do the projection over here, once we do the specific projection over here, then only we'll be able to take up all this point and calculate the maximum variance, or we will be able to calculate the variance, right? So that is the reason why we really need to project this particular point over here. So once we project, let's say if you are trying to project P1 to P1 to this particular unit vector, that is u, P1 dash, then this projection is given by an equation. Let's say if I'm saying projection of P1 on u, right? If we write the specific equation, the equation will be given something like by, we can write it as P1, that is magnitude of P1, P1 vector multiplied by u vector divided by magnitude of u. Okay, so this is the equation that is basically used with respect to the projection of a specific vector on a unit vector. Okay, and since this magnitude of u is equal to 1, since this is a unit vector, and whenever we have a unit vector, the magnitude of that particular vector will be 1, we can write the projection of P1 on u is equal to nothing but dot product of P1 multiplied by u. So this is the entire thing that we basically get. So as soon as I do a dot product of P1, which is given by this coordinate x1 and y1, and let's say this unit vector is given by the coordinate x2, y2, when we do the dot product with respect to P1 and u, I'm actually going to get P1 dash. Okay, so this is nothing but this is P1 dash. Now, this is with respect to the projection, which everybody needs to understand. Okay, now let's go towards understanding like this. When we do all the projection, let's say once we project P1, we will be getting P1 dash. Let's say there will be another point. Let's say this is P2. Then we'll be getting P2 dash. Then we'll get P3 dash. Then we'll get P4 dash, right? All the points, we will finally project it. Let's say P0 dash. Like this, we have all the points and we get finally Pn dash. Now, once we have all these points, and remember, whatever value we get from this particular dot product, it is a scalar value, right? And when we can take up all the scalar values, so this all values that we are going to get after projecting it, this all will be a scalar value itself, right? Scalar value itself. Now, once we have all these values are basically talking about the distance. Let's say, what is P1 dash basically talking about? It is just talking about the distance from here to this particular axis, right? So let's say if I'm probably calculating distance from origin to this, right? It is basically talking about this specific distance, right? P1 dash. Similarly, P2 dash, suppose if this is P2 dash, I'm basically talking about this distance, right? From here to P2 dash. Now, once I have the scalar values, then it becomes easy for me to compute the variance, right? Let's say these are all my points. So I'm just going to select all these things, okay? And these are my points, P0 dash, P1 dash, P2 dash, P3 dash. So let's say I'm talking about the specific points. Let me give us some different notation so that it becomes easy for you to understand. So let's say this is x0 dash, x1 dash, x2 dash, x3 dash, x4 dash. Like this, I have xn dash. Okay. Now, in order to compute the variance, I can simply use an equation that is summation of I is equal to 1 to n. And here I will specifically be using, how do you calculate variance? You will be able to take x of I minus x of I, this will be x bar, which will be the mean of x whole square divided by n. So if you use this equation, you will be able to calculate the variance. And understand here, your main aim will be to find out the unit vector, the best unit vector which has the maximum variance. Your goal is basically to find the best unit vector. And how do we say best? Because it captures maximum variance. So this is the example with respect to this, what we have actually discussed. Here at the end of the day, we are trying to find out the vector which captures the maximum variance, right? So this basically becomes our cost function. So here I'm just going to write max of variance. We have to find the max of variance. So in short, we have to find the best unit vector which captures the maximum variance, right? So this is in short an understanding where you are taking care of two things. One is projection and one is the cost function, wherein you are focusing more on getting the maximum variance, right? Now we will try to understand. Now see, obviously we cannot keep on go ahead and selecting different units vectors and probably trying to find out the best vector in that way. So what happens is that there is a technique which is called as eigen decomposition, which we specifically say as eigenvectors and eigenvalues. Suppose, okay, this eigenvectors and eigenvalues, because our main aim is, as said, right, we really need to find out the unit vector, right? Whether the unit vector should be this, or this, or this, or this, right? So how do I find out which unit vector we should basically select to capture the maximum variance? So for that, we will be using something called as eigenvectors and eigenvalues. And there are some steps, right? That are steps which are involved in this. First of all, the first step will be that I really need to find out the covariance matrix between features. And in order to find out eigenvectors and eigenvalues, what I need to do is that this eigenvectors and eigenvalues will be computed or will be found out from this covariance matrix. How? That we'll discuss about it, don't worry. And whichever eigenvector will be the largest one. When we say the eigenvector which is largest one, that basically means for the eigenvector where the eigenvalue is high. This eigenvalue basically talks about the magnitude of the eigenvector, okay? So this eigenvalue is nothing but, this is basically the magnitude of the eigenvector. This will basically capture the maximum variance. And this is mathematically proved, guys. I will not be proving you this thing, but here according to linear algebra and with some of the mathematical equation, we can definitely prove this. So in order to, why do we compute eigenvectors and eigenvalues? Because see, at the end of the day, I really need to find out the best unit vector such that maximum variance is captured. And we cannot keep on doing hit and trial, right? So what we do is that in order to find out, we really need to go ahead and find out eigenvalues and eigenvectors. Sorry, eigenvectors and eigenvalues. And the step is that first of all, we will go ahead and find out the covariance matrix between the features. Okay. Between the features, we'll go ahead and find out the covariance matrix. And then we'll try to find out the eigenvectors and eigenvalues. The eigenvectors and eigenvalues can be found out by the simple equation that is A lambda is equal to, A vector V is equal to lambda vector V. We'll try to understand this specific equation, what exactly this equation is. This is nothing but linear transformation of matrix. So we'll try to understand what exactly is this linear transformation of matrix. And then once we do this, you will be able to get some eigenvalues. Whichever eigenvector has the highest eigenvalue, which is nothing but magnitude of the eigenvector, that specific vector will get selected. If suppose this is the vector that has the highest magnitude, then this will get selected because mathematically it is proven that whenever we project on this specific line, maximum variance will get captured. Okay. So this is what we are going to do in the next step. We'll understand about eigenvalues, eigen decomposition from a specific matrix. Okay. So I hope you have understood till here. Now let's go ahead in the part 2 of the maths in-depth intuition behind PCA.